see. Okay, so the big idea here is that, you know how when we were in Algebra 2 and Pre-Cal, and we might have a parabola, and we were, a lot of times we would be asked for the maximum or the minimum value, and the minimum is the low value, and the maximum is the high value. For instance, in this parabola, the vertex would be the maximum value. Well, what we find out is that we can do this for all functions, and we can use calculus to do it. So what we find out is that we can find the minimum and the maximum with calculus. That's an awful picture, by the way. And what we do is this. The critical values, and again, we call maximums and minimums critical values. The critical values occur either where the first derivative is 0, so you take the derivative, you're going to set it equal to 0, and you're going to solve. So that's one way to find the critical values. Or it could be where the derivative basically is undefined, okay? So like how they say that in the book, looking to see how they said that. Here's why. Let me explain it to you. I can't remember how the book worded it, but I can explain it to you. Let's say I have an absolute value graph. Looks like maybe something like this, right? Remember how we couldn't take the derivative at that point because the limit from the left and the limit from the right were two different values? So even though that function is continuous at that vertex of that absolute value function, there's not really, it's continuous there, but there's not a derivative there since the left-hand limit and the right-hand limit were going to be different numbers. So that also, if you look at it, that is a critical value there. A critical value is, again, a minimum or a maximum. Again, that's all that means when you see it. So it can happen where the derivative is equal to 0. And it can happen where the derivative is undefined at a certain value, derivative undefined, or where it's undifferentiable, that's what they say, where it's undifferentiable. Okay, so it's not like, for instance, there it wouldn't be differentiable, but it might be the minimum value. And the other thing is, if you're trying to find your critical values, the other thing you have to remember is that you need to check your endpoints because, for instance, what if I wanted the maximum value and maybe I had something like this, and it's a line. And it has a line segment, or because maybe I'm just looking at part of the function. Well, my maximum value is going to be at my endpoint, right? If I want to know where, like for instance, if I wanted to know where my derivative is equal to 0, that's a line. The derivative is a slope. It has a slope. The slope's not ever going to be 0, is it? But I could tell where the maximum is because actually on this graph I can see it. It's that right-hand endpoint there. So I have to think about these three things: where the derivative would be 0, and sometimes there's not a place where it's 0, as in this instance. Where the derivative might be undefined, maybe there's a value at the function, but they can't take the derivative, like this point right here. And we also have to consider the endpoints when we're looking for things, okay? Let's do number 13, for instance. You have f of x is x squared times x minus 3. And you want to find the critical values. And so again, I'm going to take the derivative. That's one way to do it. I actually have to check three things. I have to check where is the derivative equal to 0. I have to remember that if there's any undefined points on there, or undefined, if there's any place where there's a value that doesn't have a derivative, I'll just put undefined derivative or something. I don't know. It's undifferentiable. I have to think about that. I also have to think about the endpoints if they give me just a part of a curve. Now, here they didn't give me part of a curve. If you look at 13, they didn't give me any endpoints, did they? So I don't have to think about this. That means on this one I can automatically say I don't have to worry about that. When you get down to number 19, they add that in on problem 19. All right, so if I want to take the derivative here, I could use the product rule. I prefer not to. Isn't it just as easy to distribute that and say that's x cubed minus 3x squared? And then I'd rather do that than the product rule any day. That's 3x squared minus 6x, right? So if I want to find where my critical value is, and again, I could look at this on the calculator and see it. If I want to find where my critical values are, they're going to occur where that derivative is equal to 0. So this is going to require you to do just some factoring. If you think about this, What's the GCF of those two terms? The biggest thing you could get out of both of them? 3x. So we're going to take the 3x out. And when we have like x minus 2 left over.
Mm-hmm.
Now, how do you find your solutions when you have something like this? You remember? Okay. Remember when you factor a thing, you're dividing it into its little parts. These are the prime factors of that function, or that derivative of that function. So you can look at it like this. There's two things multiplied together to give me 0. If I multiply two things and get 0, one of the two things has to be 0. That's the only way I can multiply two things and get 0. So either the 3x is equal to 0, or the x minus 2 is equal to 0. So to get my solutions here, 3x equals 0, divide both sides by 3x is 0. So there's one possibility. And then x minus 2 equals 0, x is 2 would solve that. So my critical values, since I'm not thinking about my endpoints, would occur here at one of these 2 points. If you think about it, this is a cube, right? You kind of have to think about what graph you're dealing with. A cube does something like that, doesn't it? The endpoints aren't going to matter because it goes on and on forever. The range of that thing is all real numbers, so it's not going to hit a maximum value. It doesn't have any kind of asymptote or anything like that, in other words. So when we're thinking about places where we don't have derivatives, that's other things that we have to think about. Are there any asymptotes? Are there any holes in the graph there? But we don't have a fraction, so there's not any holes in the graph, and there's not any asymptotes. This is a polynomial function. So that's why I don't even have to worry about this undefined thing here. All I really have to worry about is where the first derivative is 0, and so we get 0 and we get 2. And now I don't know what they are, but I do know they're the critical points. So if we go look, even if you think about the shape of the cubic function, maybe we go graph this on our calculator. That's what I'll do next. I'm going to have to cut this off. So you can look at your calculator and tell if these were maximums or minimums. There's no way to tell from just the derivative whether it's a maximum or minimum. Okay, on this one, if I want to know, where my relative extreme would be, which means they're minimums or maximum. Again, they don't have to be the absolute minimum and the absolute maximum. I'm supposed to say relative extrema, but this is not, stylus isn't working, so my finger's working better. And this was h of s. Now, I know one thing I need to consider. I need to do the derivative. That's one thing I need to do. So let's do that first. We'll just do the 3 things that we got to check. Couldn't I write this as h of s is equal s minus 2 to the negative 1 power, so I can take the derivative easier? Okay, so that would be negative s minus 2 to the negative 2 power, right? That is really negative 1 over s minus 2 squared. So what I do is I take the derivative and I set it equal to 0. So I'll just put the 0 over here. Is there any way that function's ever going to equal 0? No, if you just look at the numerators, on a fraction, in order for it to be equal to 0, the numerator would have to be 0. And you got a negative 1 up there, there's no way to plug in anything that could make that a 0. So this is not going to give me my maximum or minimum here. So the next thing I'm going to do is check places where it's undifferentiable. That means places like the sharp points on an absolute value, or it could be places where there are holes or asymptotes. Well, I do have something like that here. Because if I look at this function, 1 over s minus 2, I'll put the h of s over here, there is a place where that could be 0 and it would be undefined there. That means I have an asymptote there because it would only be a hole if there was a factor to cancel out with it, and there's not in this case. So at s minus 2, I have an asymptote, and if you remember about asymptotes, you take that factor in the denominator, you set it equal to 0, and you solve. Okay, so maybe I have a maximum or minimum at s equal 2. I'll check that out on my calculator in a minute. But this is one of my areas I'm thinking, okay, this must be, and it's something I need to look at. It's a possible answer. So this one actually had some information that would help me here. The third thing I got to do, since they gave me these values, this means my interval goes from, in this case, your x is like your s here, right, from 0 to 1. So the third thing I got to do is check those places, check the endpoints. Okay? So what I'm going to do is say, okay, well, what's f of 0, or I'm sorry, it's h in this case, h of 0. We're going to plug in 0. That'd be 1 over 0 minus 2 is negative 1/2. So that's the value I need to look at, is that negative 1/2. Let's see, the other one I needed to look at was s equal 2. So I'm circling all the things I got to look at on the graph in red. Now I need to plug in the other endpoint. H of 1 would be 1 over 1 minus 2, would be 1 over negative 1, which is negative 1. If I have a maximum or minimum on my graph, it's going to occur at one of those three places. So what you do now is you go, we could look at the signs on the table, but the easiest way to go from here is to get your graphing calculator and look at the graph and look at those points and identify whether they would be maximums or minimums, or maybe they're just some kind of weird extraneous thing hanging on there. Okay, so we're looking at the graph, and what it looks like is if you're just looking from 0 to 1, it looks like at x equals 0, that would be the high point, wouldn't it? Wouldn't it be like a relative on just that interval from 0 to 1, that x equals 0? Oh, wait a minute, that wasn't one of our points that we got when we did it. If I'm only looking from negative 0 to 1, do I even care about negative 1/2? Nope. Do I care about 2? It's not in this interval, is it? Not in the interval. Do I care about negative 1? It's not in the interval. So guess what I would say? There's no relative extrema here. If you wanted to get technical, the relative extrema would have to happen at, I'm so sorry.
Endpoints.
Yeah, well, actually, it would have to happen at endpoints. So it would be at 0, we had negative 1/2. At 1, we had negative 1. So there would be a maximum at x is 0, and that maximum value would be the negative 1/2. So I would have a maximum value. Here is my actual answer here. This is my maximum just because out of all those things that I had to look at, that had the highest value. That was the only thing within that little range of values there that was actually the highest value. Okay, so I kind of misspoke. I want to clear up something here. I only care about values between 0 and 1, and I didn't have a place where the derivative was 0. I did have some holes in the graph, but the holes in the graph occurred at 2. And if you think about it, s equal 2, that's like x equal 2, okay? It's not even, that if I think about that, that's not even in this interval up here, so that's why I'm going to throw that value out. Now, so it ends up being my endpoints are where I'm going to look here, and my endpoints were at x is 0 or s is 0, so that's this one right here, and the y value I got was this negative 1/2. The other endpoint was x or s is 1, which was right here, and the y value I got out of that was negative 1, which is the bigger value between negative 1/2 and negative 1, negative 1/2. Therefore, that is my relative maxima, maxima, or maximum on this interval. So we do have a maximum. I kind of misspoke a minute ago. What I did, and it's easy to do, I think, so you might want to watch out that you don't do this too, is that we're checking these x values and we're looking for the highest or lowest y value. So my highest my highest y value is this negative 1/2. It goes with this h of 0, which was this endpoint here. So the endpoints, a lot of times we don't have to mess with them, but when they show up, they can be a little confusing. So just remember, you got to do these three things. Take the derivative, set it equal to 0. Sometimes, you don't, like this case, nothing you had to do. And then, check for holes and also check the endpoints.